Hope you're all doing well. Hopefully you can hear me. Yeah, okay. We'll start here in about 4 minutes. If you want to go to the restroom, get something to drink. Got some nice tea there going on, Sophia. Good thinking, like that. We'll get started in about 3 minutes. So if you want to go to the restroom, get something to drink, get something to eat, whatever, that's fine. We'll get started here in a couple minutes. So if you'd like to get something to eat, get some drink, a restroom, okay, I think we're going to go ahead and get started. First of all, everybody doing okay at home? Yeah. I'm sure you've had a chance to hear about some of the stuff going on with AP. Honestly, I haven't kept up with it. Oh, I need to share my screen with you. Hold on a second. I have read it, but I can't remember all the stuff. I think the last iteration that I've seen is there's going to be 2 questions on your AP test. It'll be 45 minutes. I believe one's a 15-minute or a 15-point question, and I can't remember if the other one's like 10 points or something like that. I can't remember. I have to look at it again. But I just wanted to share with you that sorry, somebody's trying to get in with a name I don't know, so I'm not going to let them in. Anyway, the last day, or I should say the day of that exam is on the 11th. It's a Monday, which means the last day for you, I'm sure you've read this, is it's kind of exciting. It's like the one thing that's nice is the last day of class then would be that AP test day. Well, that's a Monday, and you'll actually be in testing then, or you'll do a test sometime then. And I don't believe in last minute, anxiety driven, "Oh, I got to study." Too late. If you haven't studied before then, you're just going to make yourself get a lower grade by rushing and cramming or whatever. So actually the last day for us is going to be May 8th, which is a Friday. Um, and so I really don't have any worries about getting through this momentum stuff, even though we're only doing like 2 days a week. So I'm pretty sure we'll get through that. The only worries I have, which is actually the same worries every year, is getting through the rotational dynamic stuff. So I'm going to tell you the first year, originally this was an honors class, kind of like there's honors chemistry. But the truth was, I saw so much overlap between the honors physics course and AP physics mechanics that I thought, well, the students who are really motivated, who will actually do a little bit of work on their own, I kind of feel like I'm holding you back by only doing honors. And so that's why students were like, hey, can we have an AP course? And so we started it. So what I'm saying is, if you're the motivated kind of student who's going to work a little bit harder on your own, if you would actually kind of look at some of that rotational dynamic stuff, that's the only thing we're missing. I think you would do well. In fact, that first year, I didn't even mention rotational dynamics to the students. They didn't even know about it. Didn't talk about it. Didn't say it was going to be on the exam or anything. I had one student who really did work really hard, and she got a 5 on the thing. And it's because of her too. It's not because of me, because that was one section we didn't cover. Having said that, there was quite a few students who got 3s and 4s on it because we covered enough material that they were fine. They didn't do any outside preparation. So anyway, I just, would like to encourage you, if, this is really important, you get a 5, I think you can get it. You just need to actually do some studies on your own and look at some of that rotational dynamic stuff. I opened up some of the checks in the AP classroom, so you could do that if you wanted to. Anyway, so again for us, the very last day of class is going to be Friday, May 8th, so that's kind of exciting. Okay, so what we're doing today is we're going to be whiteboarding the explosions in the impulse lab, so both of those labs. By the way, I just wanted to say that this is really challenging for me, doing this stuff online, trying to make sure that I'm being fair and at the same time making sure that people are engaged, because it's kind of easy not to be engaged. So the only way I can really do that in a fair way is by looking at who's participating on the whiteboards. And so I can look at the history. That's why I'm having you share it with me. I'm looking at the history, seeing that you contributed. So I understand that you want to share and kind of divide the workload, but during this time, I really need to see that everybody's contributing. So what I envision that means is that everybody's getting their data, everybody's graphing it, and you can actually work together on one whiteboard if you wanted to, but maybe when you're making the whiteboard for the graphs, maybe one person's title, maybe another person's drawing in the line at best fit, and maybe somebody else is putting the point protectors in the mathematical model, something like that. Or maybe everybody's doing that and they're kind of collaborating. I need to be able to see that in the history. And I know that's kind of hard to do. Or the alternative is you do your own and you share that with me. So I'm sorry, but I really don't know any other way to make it fair. So anyway, also I saw some people were working through some of the problems on the response sheet. Come on, you know me. I don't expect you to know this stuff. We don't ever whiteboard those questions on the response sheet until after we've already got consensus on the mathematical models. So I don't really even know if we'll look at any of those problems today. We're just going to be looking at the mathematical or the graphical models and the mathematical models to see if we have agreement. Okay, so anyway, let me check my email. I had some people email me. All right, so what we're going to look at is we're going to look at the explosion lab first. And if you remember what this was, is we had two carts and they were being triggered and they're kind of flying apart from one another. And one's going in one direction, one's going in the other direction. So one of them's probably going to have a negative velocity. So Aiden just sent me his this morning. So I think I'm going to look at his first. And we'll look at everybody else's too. We're just trying to figure out what the consensus is. So it looks like he has an inverse on his. Keep in mind, really this inverse probably would be going down. It'd be upside down because one of them's going to be negative, right? All right, so let's look at other people's. Grab the wrong one, sorry. All right, let me expand this. Oops, that's not the right one. Sorry. Maybe I clicked on the wrong one. I'm not sure. All right. Okay. So I don't even remember whose this is, but this is one whiteboard. It kind of looks like an inverse model. And again, notice it's negative because one of the velocities is negative, so the ratio of the velocities would be a negative. This one also kind of looks like an inverse. Looks like an inverse. Inverse. Kind of looks like an inverse if you just look at the blue dots, not so much the line. Hold on a second. Somebody's wanting to get in. Looks like an inverse. Again, just look at the blue dots. Kind of looks like an inverse. This one again, I believe it was inverse. It would be actually kind of upside down. You might be going, well, why didn't you make it so that the axes were upside down like that? Well, I didn't want to give you too much of a hint of what it would look like. Right. So that's why I didn't. It looks like an inverse. Again, I think it would be upside down though. Inverse, again, I think it's upside down because the two are going in opposite directions. Inverse, upside down. So if you're wondering, okay, how do I make this so it's upside down? I think you could just flip it over. Let's see, can I actually do that here? So for instance, you can just flip this over, maybe not. Like this. And what you can do is just put another axis right up here. It's an easy fix. I think it's an easy fix. And there you go. There you got your inverse. And then as far as linearizing then, what's going to happen when you linearize this is, I believe, your graph, instead of going up like this, will go kind of down, I believe. Okay. So again, the reason why I didn't give you those axes is because I didn't want to give too much away. Because there's something kind of important about this relationship we're looking at here. And again, kind of inverse, it should be kind of upside down. And I don't know, I must have picked the wrong one here for this one. All right, so I think we're all kind of in agreement that it's an inverse relationship, okay? And so then when you linearize it, you get kind of this graph here. And the mathematical model then, I believe, would be kind of negative. Actually, you could say the ratio of the velocities is equal to negative the ratio of the masses. Oh, wait a second, wait. Let's see, red, blue. Oh, yeah. So notice how now here you have velocity of red over velocity of blue, but then it's equal to the inverse of the ratio. So it's going to be mass of blue over mass of red. I personally would put the negative over on the other side because that's the slope, which is -1. And I think we probably would all kind of agree with that. The slope's -1, I think. I think everybody has that. Okay, all right. So any questions about that so far? Okay, I think I'm going to work off of this one. I'm not sure whose this is. We all kind of have the same relationship here. It's kind of difficult dealing with this ratio. What I want to do is I want to multiply both sides by the mass of the red, and also multiply both sides by the velocity of the blue. In other words, let's get rid of the ratio. And if you do that, what you get is you get the velocity of the red times the mass of the red equals negative mass. It's going to be mass of blue times velocity of blue. So I'm going to write it as velocity of blue times mass of blue. Okay, so at this point, I need to kind of give you guys so that's going to be our consensus mathematical model, by the way, right there. I need to give you a new definition for a new thing, and that new term is momentum. Momentum is sort of, first of all, I want to give you a kind of conceptual idea of what momentum is. Momentum is kind of like inertia, but it's inertia in motion. So if you want to figure out what momentum is, it's really going to be the product of mass and velocity. And so for this particular one that we have here, I should also tell you what the symbol for this is. Momentum, the symbol is P. I used to know the reason why that was. I think the Latin term progress, P stands for progress. And so I think the Latin term that, I'm not sure if it was Newton that came up with it, but he's the one that first named it, I think. I think it was Newton. And then he used the Latin term progress for momentum. And it's going to be equal to m times v. Now these are both vector quantities, so I'm going to try to put a little vector notation above them, if it lets me. So p is a vector, and the velocity is a vector. Or I should say momentum is a vector because velocity is a vector. When you're thinking about those cars, I'm going to kind of draw a little picture here. The cars that are kind of shooting away from one another. The blue one and the red one, and I don't really remember which one was on which side. But they're kind of, shooting away from one another like this. I want you to think about this momentum that both of them have. That's really the final momentum. In other words, up here, this momentum that we're talking about, this was the final momentum of the red car, and this was the final momentum of the blue car. What was the initial momentum of both of them? If somebody can turn on their microphone. What was the initial momentum before they exploded away from one another?
Would it be zero?
Yeah, it's just zero. Yeah, it was just zero, right? Because the velocity was zero, right? So I just kind of want you to think about that. All right, so I think I'm going to stop there. I know we haven't done any of the problems. That's okay, because I just want to go on and look at the next lab. Any questions on this one? So we now know what the graphical model should look like, so you might have to change your graphical models. And we also know what the mathematical model should look like, and I've given you this new definition here, okay? All right, so now we're going to look at the impulse relationships. So the impulse, if you remember with this one, there was this astronaut, and I don't know if they had a rocket pack or what exactly, but you turn on the rocket pack or whatever it was, some canister they're holding, and all of a sudden they start shooting the other direction. And they go through these two photo gates. And so the photo gates help you figure out what the velocity is, because you know the distance and you know the time. It's kind of like a stopwatch. And then you could figure out what that final velocity would be. It also tells you what the force and how long you're applying it and everything is. So one of the definitions I gave you before you started the lab was that impulse is equal to the area under a force time graph. So this is a little bit different than, I mean, back for energy, we were already looking at force position graphs. So for instance, like let's say a spring. So we had a force of the spring and we had X down here, and the graph looks like this sort of, and we called that area underneath here. Let's see if I can draw it. Well, that's kind of cool. Let's see, triangle, 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 triangle. All right, fine, whatever. I'll just have to rotate it around. So this area here, this was called the energy. So this was the energy that was stored in it. So that was energy. Well, in this case, we're not looking at the force position graph. We're looking at the force time graph. So not so much a spring. Think about it as, let's say you're punching a pillow. So how much force you're putting into the pillow and how long you're touching the pillow. So force and time, and it could look like this. The graph doesn't have to look like that though, by the way. Maybe I'm thinking if you're hitting a pillow, it probably is going to look something like this. Not exactly like this, but there's going to be like a maximum force, and eventually you're going to go all the way through your extension and the force gets smaller and smaller. So it's probably going to look like that. The area for this graph is not energy. This is called the impulse. Okay, so that's what impulse is. Did I spell that right? Yeah, I think I did. Okay, so if this was, let's say the graph doesn't look like this. So let's say the graph looks like this. Let's say it's a constant force. Well, that's really easy to figure out what the impulse is. It would just be force times time. And that's sort of what was happening in your lab. You had a constant force in a certain amount of time. And so it's really easy to figure out what the impulse is. Okay, so anyway, you were trying to figure out what's the relationship between impulse and this new quantity, m times v, which happens to be called the momentum. And so this group here, and again, I'm sorry, I don't know which group this is, but anyway, this group here had, it looks like a direct relationship. This group here had a direct relationship. Direct, 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 direct. I'm not sure what happened there, so I'll get rid of that one. This was direct. I don't know what happened there. Okay. And then I probably should look at Aiden's here, impulse. And also had a direct relationship. Okay, so it looks like we all agree that it is a direct relationship. So now that means it's going to be mass times velocity equals whatever the slope is times the impulse, which is force times time. Sometimes you'll see the variable for impulse is J. I don't usually use it. I just use F times T. But on the AP test, you could see possibly a J for impulse. So now let's talk, it looks like this was direct relationship. It looks like the slope here was 0.85. This group here had a slope of 0.952. Slope here was 1.009. Slope here was, ooh, that's a big number. 20,000, I think. 20,000. This one's 1, it looks like. Looks like the slope here is around 11 or 12. Didn't get an equation. Looks like the slope there's 1. Looks like maybe the slope's 1. I'm not positive. So there's 1.04, 0.085, and slopes 1. So we're kind of all over the place there, but it looks to me like most groups are getting a number close to 1. Not all groups, but a lot of the groups are getting a number pretty close to 1. So probably some of the other groups, you probably ought to go back and look at your data. I can't remember if they gave you some units that were unconventional. Can anybody speak up? Is there anything that you guys noticed that might mess up what your data would be?
The units seem to be 1/kilograms. I'm not sure if that.
Oh, okay. So you had to worry about that. All right. All right.
I didn't even graph the right thing on accident.
Oh, okay. All right. So let's see. I think I'll go back to this one here. So this number is pretty close to 1. I think we'll go ahead and go with this. So I want you to understand that this momentum, this MV, this is not the initial momentum. Think about it. This was the astronaut. Before you turned on the rocket-propelled pack, what was the initial momentum? Anybody? Turn on your microphone.
0.
It was 0, right? So really what you're looking at here is the final momentum. And so this impulse is equal to the final momentum, but only if the initial momentum is 0. So that's kind of interesting. What that means then is that the impulse, force times time, impulse, is equal to not momentum, but a change in momentum. In other words, impulses cause changes in momentum. So I think I'm going to use the symbol J for impulse because, yes, in this case it was force times time, but if your graph looks more like this, then I wouldn't say force times time. I'd have to use the area of this, which would be like 1/2 the height times the base. Or if you have some kind of strange graph, let's see if I can draw this. I'm not sure if I can do it. Let's say you have some kind of weird graph. Oh no, it looks like I'm flattening the curve. So if we have some kind of weird graph here, if I want to find the impulse, I have to find the area of that, which means we have to start doing a little bit of calculus. That's going to be integration. Okay. But anyway, oops, I messed that up. I can get it to stop. All right. So I'm just going to use the letter J for that. Again, usually I don't do that. So the impulse is going to be equal to the change in momentum, and I'm going to use a symbol for momentum P, and I'm going to have to draw in here a triangle if I can, because I need to get the symbol, the delta symbol there. So transparent. So it's equal to a change in momentum. I want you to understand that, again, momentum is a vector quantity. So that means that change in momentum is also a vector quantity. So change in momentum is a vector quantity, and that also means that impulse is a vector quantity. So both of these are vector quantities. So if you remember, vectors are kind of a pain. Sometimes they're harder than other times. So for instance, with forces, they're pretty, they're kind of a pain because you have to do all the force diagram stuff. Kinematics, yeah, wasn't too bad. Momentum's kind of somewhere in between. It's not as hard as dealing with force diagrams, and it's kind of in line with kinematics. In my opinion, momentum's actually kind of easy, except actually it's still easy, but you just have to remember that sometimes you have a change in direction, so something's got to be negative, just like with kinematics. If your velocity's up and your acceleration's down, something's got to be negative. So if you stay aware of that and make sure you put those in your calculations, you'll be fine. It's pretty easy stuff. Okay, so I I think then we've covered everything that we needed to cover. So now you understand that impulses cause changes in momentum. Impulse is not equal to final momentum. Impulse is not equal to initial momentum. Impulse is not equal to momentum. It's equal to change in momentum. It causes changes in momentum. They're both vector quantities. They're not scalar. And just remember, the way you find momentum, it's equal to m times v. So maybe I should go a little bit further with this equation. So the impulse would be equal to mvf minus mvi. And if it's an easy equation where the force doesn't ever change, it's really going to be force times time equals mvf minus mvi. Pretty easy equation, not too tough. Okay, any questions? So how long has this been going on? Hey, we're doing okay in time. All right, so let's see. I don't think I have any questions. All right, where are we at here? Okay, let me get rid of these. And let me get rid of that. And let's see. I think what we're going to do, because I don't want to do too much, is I think we're going to stop right there. You do not need to worry about, we're not turning this lab in yet. We're still need to whiteboard both of these labs. There's other questions on them. You could try them. Feel free to try them. But of course, I'm not holding you accountable for that because we're just learning this stuff, okay? We still need to whiteboard it. But I need you to also take this attendance quiz. And so that means I need to give you the code. So let me go ahead and give you the code. The code, by the way, this quiz is kind of over what we just whiteboarded. The code is right here. So you probably want to go ahead and copy down that code. Shouldn't take any more than 15 minutes. You have to get 100%. So if you want to take it over and over again, you can. I hope that you don't have to. Should be pretty simple. And then probably on Monday, we will continue whiteboarding this. Only after we've whiteboarded the entire thing, then I'll expect you to turn it in, okay? Any questions? Okay, I want you to stay around because again, I have to give participation points, so I have to kind of see who's all here, and I need to make note of it, everything. So again, there's the code again. So I'm going to stop sharing. And I think the easiest way maybe is just to do a little screen capture here, snipping. Yeah, I think I got everybody in there. Okay, any questions? All right, stay safe, healthy. Is everybody doing okay? Nobody's sick in anybody's family? Okay, all right, good. All right, thanks for coming. See you on Monday then. Bye.
Thank you.